So we're looking at dropping a penny from the Sears Tower, which is 1,730 feet tall, and our position of the penny, its height from the ground is given to us with this formula, where S of t is height off the ground, and t stands for seconds since we dropped it. So we're going to first fill out a table here, which the long, slow way to do that would be to take one at a time and substitute each of these t values into our formula. The quicker and suggested method would be to enter this formula into your calculator and y equals and go look at the table, and you will be given that all in one push of a button. Okay, so that should be your values for the S of t. All right, so how far above the ground is the penny when 7 seconds have passed? So we just go to our table and look. After 7 seconds, it's 946 feet. How far has it fallen when 7 seconds have passed? Well, we dropped it from 1,730 feet. It's now at 946. So it traveled 730 and 54 is 784 feet. Has the penny hit the ground at 10 seconds? Well, at 10 seconds, our value is 130, so no, it hasn't hit the ground. Okay, and our justification is simply because the penny is still 130 feet above ground. Now we're going to go a little bit sideways here for a minute. It will have a purpose, but the average rate of change of an object is given by this formula. Now this is the dirt formula, the distance formula that we usually write as d equals r times t. It's just rearranged and solved for r, okay, for rate. It can be used here to solve for any of the variables if you have two of the other ones. The example here says if we drive 225 miles away and an average of 75 miles per hour, we could just divide 225 by 75, and the answer is, oh, it takes us 3 hours to get there. Okay? Now, if your mother finds out that it took you only 2.5 hours, she's going to be angry. Why? Well, remember, what changed here was the time. The distance away hasn't changed. So if time equals distance over rate, I'm sorry, we don't want to use that formula. If we go back to r equals d over t that was circled up at the top, our distance away hasn't changed, 225 miles, divided by, if it's now 2.5 hours, Mom's going to be mad. Well, why is that? Well, if we figure out the rate that we averaged here, we were averaging 90 miles per hour. So using the formula to explain why, we would have to average 90 miles per hour. So how is the slope formula like the formula for rate? Well, in order to find any distance traveled, we would have to subtract, sort of like we did when we subtracted how far has the penny fallen after 7 seconds. We subtracted where it started and where it ended up. So you would subtract two distances to come up with your total distance traveled. And how long did something take? Well, you would subtract 2 times. What time did you start? What time did you end? And that's how you would arrive at the total travel time. So if you thought of time as your x value and distance as your y value, you are just doing this slope formula. You subtract the 2 distances, divide by the difference of the 2 times. So using that, find the average rate of change for the penny on the interval from 0 to 1. So 0 to 1. If we are using it sort of as a d1 minus d2 over t1 minus t2, it's what were the two distances? Well, from time 0 to time 1, we went from 1730 to 1714. And in times, we went from 0 to 1. So we traveled 16 feet in 1 second. Now, technically, that's a -1 because we get a negative rate of change anytime something is going down, but we're not really interested in the negative right now. So our average speed was 16 feet per second. Do the same thing for the 6 to 7. Well, 1154 minus the 946 divided by 6 minus 7 gives me 208 over -1. So we're going to say that's 208 feet per second. Now, if you think about what you're doing as we do it, that means for that first second that the penny was falling, it was averaging only 16 feet every second. By the time it had been falling for 6 or 7 seconds, or between that 6th and 7th second, it was averaging 208 feet per second. Okay? That word for that is acceleration. It had really, and it continues to accelerate. So I guess that's the answer to number 9. Why does that happen? Why is it so different? Acceleration. Why is it accelerate? Gravity. So what's the average speed for the whole table from when I let go till 10 seconds later? Well, that means I would have to do, I started at 1730. After 10 seconds, it was 130 feet. Divide that by the time, which again, the negative is irrelevant to us. What's interesting or significant here is just that it took 10 seconds to get that far. So we averaged overall for this penny 160 feet per second throughout that table. On just the last second that we have in the table, from 9th to 10th second, the average is much greater though. So 434 minus 130 over 9 minus 10, we get 304 over -1. So we would call that 304 feet per second. Remember, this is the average for the whole table. This is what it was at its fastest in that last second. So let's go back to your table and look at the first differences. Okay, so 1730 to 1714, that goes down 16. Then we went down, 1434, down 48. Then it goes down 80. And then it goes down 112. And then it goes down 144. And then it goes down another 176. And then the next first difference is 208. And the next one, -240. And the next one, -272. And then lastly, -304. So, what do these differences tell you? Well, look, when we figured out the average speed from 0 to 1, it was 16 feet per second. When we did from 6 to 7, we got this number. When we did 9 to 10, it was this number. So these first differences, the first differences are the average speed for that second. So take the difference of the first differences. This we're calling second differences. So this is down 32. Now, is that a surprise? I hope not. I hope it's certainly not a surprise that it's a constant second difference, because this is a linear pattern. This is a quadratic function overall. But the answer, negative 32, is the acceleration rate on Earth. So every second that goes by, that penny picks up another 32 feet per second to add to its speed.